Good morning everyone. Thank you for joining Mr. Ish for this third video on integrals. We will continue the concept of integrals by talking again about Riemann sums. Riemann sums is an important concept because it helps you understand the base understanding of what integral calculus is all about. And you know, one of the main aspects of integral calculus is calculating areas below a curve or calculating the difference of areas. As you've known, I've presented a situation where you are given a curve. Everything is above the x-axis line, and you are given a procedure for calculating the area over here. It's not hard because everything here is in the positive zone, so you can easily do it. The area over here can easily be calculated using the Riemann sum concepts, or you can just do it right over here in terms of integral calculus process called integration. You can do it that way. You can also do it using the Riemann sum process. Limit as n approaches infinity, a cumulative effect of sums from the first rectangle to the nth rectangle, f of xi multiplied by delta x, where the f of xi, the sample value, which could be representing the right endpoints, the midpoints, the left endpoints, these right here are called sample points. The sample points are plugged into your function and you get a length value. These cumulative lengths are added, multiplied by the width of the interval, which represents your width, and you can get your area that way. We've also seen examples where you can have a situation something like this. First, second, third, fourth quadrant. You can have a curve which can come and hit any of these quadrants. If your interval is like from here A to B, you can have a negative area over here, and then you can have a positive area. If you are willing to accept that there's such a thing as a negative area here, you know your area is going to be the difference of areas. If this right here is A2, this right here is A1, you're looking here at the net effect. You're looking at net areas, or the difference of areas. Here you're looking at a combined area of just a single area because it's all in the positive zone. Here you have partly in the negative zone, here you have partly in the positive zone. Again, in all of these aspects you can draw Riemann rectangles. These rectangles, and you can get their lengths, you can get their widths as through the procedure. You know, in every of these cases you can do all of that. You can do all of that, get the individual length based on the intervals, based on your sample points, and run everything through, and you can get your cumulative effect. You know, when you're doing the Riemann sums, and if you already knew how to do integration, if you were to compare the two, the area that you determine for whatever curve you're talking about through the integral process is always accurate. That's just how it is, because it truly accurate what the area is with regards to that curve. But if you're calculating the area using these Riemann sums, and let's just use RS for Riemann sums, it's not 100% accurate, it's just an approximation. That's all what it can be. Why? Because you're using these rectangles, and those rectangles in terms of their corners on the top with regards to the curve, because you don't have a corner or a edge, the top edge of that rectangle, which adapts clearly to the shape of your curve. But because of those failure to adapt, you have an approximation only, but not a true area representation. But even within the Riemann sums, you know now that the midpoint values, these sample points which represent the middle of that top edge, is what leads to the best approximation. The right endpoint sample points, the right sample endpoints lead to an overestimation, and the left sample endpoints lead to an underestimation of that area of the curve, or the net area, or the difference of areas. So keeping all of this in mind, we're going to do this video. We're not going to be talking too much about these type of subjects, these type of specificities here. We're just going to be talking about Riemann sum application and how we can interconvert between a Riemann sum application into an integral application, or how you can look at an integral application in terms of its Riemann sums, like a limit of sums. And I've told you before, integrals represent, in terms of a limit, a special kind of limit, and that is a limit of sums. So we're going to be looking at how we can look at integral functions as a limit of sums in the remainder of this video. I'm going to be presenting some example questions from a single variable calculus book I have over here, and the question will basically be not hard. We're not going to be taking these to completion in terms of solving them. We're basically going to learn how to set up expressions. Setting up expressions means how you can come up with an expression that will kind of incorporate the Riemann sum technique into the integral technique. And when I set this up, you'll see what I'm talking about. If the question is this right here is your function, and the question is this, you have to set up this expression as a limit of sums. You have to demonstrate how this integral question can be expressed in terms of a limit of sums, and you know what we're talking about. We're going to be applying the Riemann sum technique over here. We're going to somehow convert this expression over here into a Riemann sum expression. And how do we do that? And without even having to worry about the net area or the total area of the curve, and we're not even talking about graphing over here. Let me show you. The first thing you want to do always in these type of questions is you want to start looking at the things which are represented in the formula. Look, the formula for a Riemann sum, you know, is always this: limit as n approaches infinity. You have your first rectangle up to your nth rectangle, f of xi and delta x. What's the first thing you can easily come up with over here is the delta x. And you know the formula for delta x is this, is equal to b minus a over n. But I haven't even told you what n is. So we have a variable over here. What's b and what's a? B is the higher limit, a is the lower limit. 5 minus 2 is a 3. And we have a 3 over n. Because we don't know what n is, we could look at this curve. You know, if I remember correctly, x to the square looks like a curve like this. X to the fourth will be a little more broad. And you're looking at some area over here between 2 and 5. You're looking at this. You could infinitely put any number of rectangles over here. So that's a representation here is n. We have n number of rectangles over here. Anyhow, what's another item we can look at over here? We can look at this part right over here, the xi. We need to find out what our sample points are. Now, if supposedly your first sample point is a 2, because that's what it is a 2. Your interval starts from 2. Your next sample point will be how far away? It'll be exactly the width of that interval away. Look over here, 2 plus 3 over n. What's your next sample point going to be? Exactly another delta x away. Well, wouldn't it be 2 plus 3 over n plus 3 over n, which is what? 2 plus 6 over n. You see where I'm getting at? X3 will become 2 plus 3 over n plus 3 over n plus 3 over n. You say 9 over n. Anyhow, the ith point, which is representing where the last rectangle will be. The ith or ith, however you want to pronounce it, will be what? It'll be 2 plus 3i over n. Look over here. You are basically compounding intervals upon intervals by equal widths. 3 over n plus 3 over n, 3 over n plus 3 over n plus 3 over n, 3 over n times whichever number you're on. If you're on the fourth one over here, the fourth interval will be 2 plus 3 times 4 over n, right? Which will become 2 plus 12 over n. And that's exactly what this I is representing. Which interval number you're on is multiplying by that 3 over n. So now you've actually even gotten this value over here, xi value, which you will feed into your function, and then we will end up being able to express this integral as a limit of sums. And I'm going to show it to you. Let's do it right over here. How would we write this as a limit of sums? This is how we're going to do it. It's going to be presented in this limit as n approaches infinity, the first to the last n. Now, due to space limitation, I'm going to write the rest over here. What's our function over here? It's x to the 4. But what's our sample values is represented by 2 plus 3i over n. And look over here, to the power of 4. Why? Because we have a function here to the power of 4 multiplied always by delta x. What's delta x? 3 over n. Now this right over here, what we've done over here is we've taken our integral and we've represented here as a limit of sums. A limit of sums that is representative of a Riemann sum expression. But you can see how we've converted this form into this form, and that's all the question was asking you to do. But hard part is perhaps determining of this determination, which is really not hard. You just take the upper and the lower interval divided by n, because you don't know what n is. This also is slightly tricky to understand. It's always starting from x, so what your first interval is always going to be the start of this lower limit, and you're gradually adding the midpoints of each interval on that, right, and the delta x, the length of each interval, until you're coming up with some expression for an xi, which will be fed into your function, original function, and that in its totality will give you your limit of sums expression from an integral form into a Riemann sum form. Now we'll be looking at more of such examples. As we look at through more of these examples, this whole process of converting this into a limit of sums will become easy, because you'll see sufficient number of examples that you'll understand how we're going about this. This is going to be another interesting question right here from this textbook on single variable calculus, where we are given an integral over here and we have to express this as a limit of sums. The purpose for these type of questions is that they're giving you a base understanding of how the integral expression relates to the Riemann sum expression, in that they are both giving you the same eventual outcome, whether it is the area under the curve or whether it is the difference of the two areas or the multiple areas that are involved, some being part below the curve, some being part above the curve. Anyhow, when you do these type of questions, it shows you how these two types of forms, the integration form and the Riemann sum form, interconvert. If you're looking at this expression, we have to convert this into the limit of sums. The first thing you want to do is look at this delta x, the interval. That's the first thing you want to study, because that's the first easiest thing you can do. You have b and an a value, and you know delta x is always b minus a over n. You don't know what in any of these instances what this Rn is. This is what we kind of get, an expression that will help you in terms of developing the Riemann sum expression from this. The b over here is 2 pi and the a is 0. 2 pi minus 0 is a 2 pi, but it's 2 pi over n. Now the next form you want to do is look at some in terms of the sample points in terms of the intervals. If your first sample point you had was some sample point, the 0, you know for this first sample point the lower end of the limit is a 0, and x of 0 is just 0, x of 1 is just the same number but an interval away, but this interval away. It will be 0 plus 2 pi over n. The next number will be exactly the previous number, but again the same interval away. In here instances over here, the 0 after the first expression is basically meaningless. It's just 2 pi over n plus 2 pi over n, and you know what you get over here, 4 pi over n. The point which you will begin to notice over here is the eventual, or whichever value you're looking at in terms of what will be played into your expression over here for the length determination, will always be 0 plus 2 pi I over n, or 2 pi I over n. If you're looking at the 10th term, meaning the 10th rectangle in this curve, it would be 2 pi times 10 over n. N being whatever sum you're looking at, if you were given that value over here, but we're not. So now all we have to do is get the actual summation of the limits. Look over here. Let's just put the formula over here. Limit as n approaches infinity. We have, starting always from the first term to the nth term, we have f of xi, which indicates your length, times delta x, which indicates your width. And we know what has to be plugged in here. This is our xi over here. See, this is our xi, which will be placed into the function to give you your length, and you already know your width. That's your width value. So let's come over here and actually place the expression. We're going to place the expression over here as this limit n approaches infinity. We have I equals 1 and then n, and now our actual expression will be 2 pi I over n square times sine of 2 pi I over n. You see this? This right here represents all of this. All of this is going to be multiplying by your delta x, 2 pi over n. And that right there will be your final expression. This integral form written in the limit of sums. Now let's look at this other expression right here. This is another integral expression where you have to convert this into the form where you have the limit of sums in the Riemann form. And you know over here we're going to follow these type of points over here. What's our delta x going to be over here? It's going to be b minus a, 6 minus 2, 4 divided by n, because we don't know what n is. The other item we're going to start looking at is our sample points in terms of the intervals. Look over here, the sample point over here, the first point is basically just a 2. The next point is going to be the first point but this interval away, 4 over n away. The next point will be exactly the previous point but another interval away, 4 over n. If you're looking at it, you're seeing 2 plus 8 over n. Anyhow, the pattern you'll begin to see is whatever any point that you're interested in, any point is always 2 plus 4i over n away. That's always what it is, 2 plus 4i over n. If you think about it, if you're looking at the 0 point, you do 2 plus 4 times 0 over n, which will just give you 2. If you're looking at the fourth point, you'll have 2 plus 4 times 4 over n. You will have 2 plus 16 over n, and you can see it follows the same scheme as you're seeing over here. So basically our interested value over here is this in terms of plugging into the formula over here. Now let's actually plug everything in over here and let's finish this question. We can do it, let's do it right over here. We have all of this limit n approaches infinity, I equals 1 and n, and f of xi right here. This is going to be placed into your f of xi into this form over here. Now things are going to get a little cramped over here, but let's try to be neat about it. This is what we have to plug in right over here into places of x over here. You have 2 plus 4i over n over 1 plus 2 plus 4i over n. This is to the power of 5 because x to the power of 5. All of this will multiply by your interval, which is delta x, which is 4 over n, and your answer will be completed. So you can see it. 2 plus 4i over n, you can even parenthesize this numerator because that represents this x. Then you have 1 plus x to the 5, which is over here, represented with its xi. This is f of xi times 4 over n, which is your interval. So this question over here is completed. It's not hard. Now let's look at this and let's convert this integral expression into this limit of sums. You know, the first thing you want to do is basically determine your delta x. Delta x over here is going to be b minus a, which is 10 minus 2, which is an 8 over n. I was saying 10 minus 8, but it's 8 over n. That's your delta x. If your first point over here is going to be point 2, your each succeeding point will be 8 over n units away. You see this 8 over n units away? And any interesting point or point that you're interested in, or which is called the sample point xi, will be 2 plus 8i over n in terms of its distance away from the very first, or in terms of its interval level that you're talking about. When you put everything into this expression form, your final answer will play out as this. Limit as n approaches infinity, you will have the following answer layout. 2 plus 8i, this is right here your f of xi part. You're always putting, this is right as 8i over n plus 2 is the same thing as saying 2 plus 8i over n. This right here is your f of xi, but you have to put to the power of 7 multiplied by your delta x, which is 8 over n, and this question again is done. It's not a hard question at all. We look at one more of this type of form, then I'll show you something different in terms of the concept of the Riemann sum, and that'll be pretty much it for this video. This right here will be proving to be an interesting question. You have to convert this form into the limit of sums. When you're seeing questions like that, you're basically converting a limit expression from the integral form into a limit expression which is in the Riemann form, and you start by calculating the interval width, which is right here delta x, which is always b minus a over n, and here b minus a is a pi minus 0, which is just a pi over n. You don't know what n is, so your interval width is pi over n. The very first value, which would be the first value of your interval, would be just the 0. The next value would be 0 plus pi over n units away, and you can see the next unit over there will be 0 plus pi over n plus another pi over n, or you can just say 0 plus 2 pi over n units away, such that you can say that the interested value of the sample that you're looking for will always be 0 plus pi I over n units away, or you can just say pi I over n, because the 0 here is meaningless, right? This right here represents your this value over here, which you'll plug into this expression over here in terms of f of xi. See, this right here is xi. So your final answer over here will be in this form, the limit of sums. These questions are not hard. There's basically just a template you have to follow, that's all it is. It's going to be this f of xi, which will be sine 5 pi I over n. Now you're wondering where this 5 is coming from. It's right here 5, and this right here x right here, okay, times delta x, which is pi over n, and this right here is your final answer. So now that we've looked at the concept of limit of sums and how we can derive those using the conversion between the integrals to the Riemann sum templates, let's look at this other concept over here. If you're looking at various functions, you can somehow get a rough idea of where the area is with regards to its dimension. If you do the exact calculation with integration or Riemann sums, you can get a very good value of what the value of that area is under the curve, or what the value is with regards to the difference of the areas, whether it's below or above the curve, for those type of questions. But if supposedly you just want like rough ideas of where your area lies with regards to what's the lowest possible area and what's the maximum possible area. Well, we're going to be talking about that over here. For any function, there can be a certain minimum in terms of its height and area, and there can be a certain maximum in terms of its height and the potential area for the area under that function for those values of x which are larger than or greater than or equal to a but less than or equal to b. And I'm going to talk about that with regards to these two graphs, and you'll know what I'm talking about. If you had a certain function and you wanted to have just a rough idea of where or what the area is, you can say that the area is no less than this, but it's no more than that. This is what I'm talking about, where you can give that type of a rough estimate that the area is no greater than these units, but it's no less than these many units. If you look over here at this for a certain function, if you trace it between this interval of a comma b, you know over here we're talking about a comma b, the interval. For those values of x which are larger than or equal to a but less than or equal to b, hence we have this little statement over here. For this interval over here, if you take this interval and stretch it out vertically, you can see within this little interval where the function is at its highest point. The highest point is over here, and you can draw a horizontal line, and that can represent like a maximum, a capital M. Within the same interval a and b, you find the lowest point, and you connect another horizontal line across that represents the lowest point of that function, or the lower m, lowercase m, and that can be your minimum. Likewise over here, if you're looking at this in a graph of y is equal to root x, you know, a radical graph between this interval of a up to b, and for all the values of x between a and b, including and up to both a and b, you can see within this interval the lowest point of this function will be right here, just within the interval. We're not looking even over here because we're bound by the values of x between this interval, and the highest point over here. For this lowest point, if you draw across a horizontal line, it gives you a lowercase m, or a minimum. And for the highest point of this interval, you draw a line across, it gives you the maximum or the highest point of that. Within these values of this minimum and this maximum, which you know if you're looking at it from an up and down direction, you're kind of talking about the length, right? Because an area of a rectangle is always length times width, and if you're looking at the interval across, you're basically looking at something kind of like a width. If you did length times width, you'd get an area of a rectangle. But when you look over here, you see there are two rectangles forming. You see this like little lower over here, this lower rectangle, right? This lower rectangle represents the area of the minimum right here, the minimum. This right here. This right here represents your lower extent of the area of the items below this curve. And you see this other rectangle which forms over here, the larger rectangle, right here, it represents your maximum. So you have a minimum over here area and you have a maximum area. Now let's switch over here. Within this interval of this and this, we have two rectangles which form. We have this rectangle over here which forms. Let's shade it over here to differentiate it from the larger rectangle which forms over here, and we'll keep that unshaded. So in each of these cases, bounded by the intervals of a and b and these vertical intervals, minimum and maximum, where a and b interval represents kind of the width, and the m and the lowercase m and the capital M, which represent the length, kind of similar to as what we had f of xi, the length representation, and this right here is your delta x, your width representation. In each of these cases, we're seeing two rectangles form, a lower or a smaller rectangle and a larger rectangle. So let's just word it out as this, the smaller rectangle, and let's call it, symbolize it as this, okay? And let's write area of our function, and then let's do this, the larger rectangle. Now let me say this in words so you know exactly what I'm talking about. For any function which has a minimum height and a maximum height within a given interval defined by a and b, the representative area or the estimated area can be no smaller than the area of the smaller rectangle which forms, and it can be no larger than the larger area of the rectangle that forms. So therefore the true area for that function, or the true area for the area or the part below the function, remember the area under the curve, the true representation or the true value for the area under the curve is within this interval of the small rectangle area and the large rectangle area. And we should be putting here area over here for a over here for the areas, okay? So if that didn't make sense, and I'm going to show you a few examples of this, I will say it again. For any function which is defined as y is equal to f of x, the area under the curve. Or let's also say for those instances where we don't have an area under the curve, but this is primarily for areas under the curve where you have positive intervals. For the area under the curve, it can be no smaller than the smaller rectangle area which is created and no larger than the larger rectangle area that's created. And I'm going to show you this numerically with a few examples, and we'll close the video with that. And for these type of questions where you're just estimating the interval within which the true area lies, the minimum and the maximum area, you don't have to do any graphing. The whole purpose of the graphing I was showing you prior to this example was just for the purposes of this video for understanding. Now look over here. The formula you have to follow over here is not hard by any means. You have to find that minimum value, the minimum length value, and you multiply it by your interval width. Remember, length times width is always an area, right? Length times width. And your function area will fall within that interval. And we can even give this a representation of that interval, and it will be less than or possibly equal to the maximum length that you're noticing multiplied by the interval. The interval values will always be the same. It's these lowercase m and the capital M values which will change. So where does a true area for this, if you didn't know integration, where is a true area for this function, where does it lie? And we can do it like this. Always calculate the b minus a value first. B minus a, because that's easy. What's b minus a? It's 4 minus 1. 4 minus 1, so it's 3. Now we have to calculate the lowercase m. And then we have to calculate the capital M. How do we calculate the lowercase m and the uppercase m? Remember again to this specific point. What does length always mean? Length. Length is always represented as f of xi. Your sample point placed into your function gives you your length. And that's exactly what we're talking about here. What's our sample point over here? Well, it's a minimum value, 1. You place it in the function to get f of xi. We're talking about here f of xi. What does that mean over here? We're talking about root of 1. What does that mean? 1. See, you're putting 1 in here. Now the maximum over here, length will be again the maximum value of your maximum sample value placed into your function f of xi, which will be root of 4, which will be 2. Now all you have to do is write this into this representation, and that right there is your final answer. Your final answer is this. The area for this specific function can be no smaller than this. You'll do m 1 times interval, 1 times 3. 1 times 3. This is right here your m, lowercase m times b minus a, 1 times 3. Less than or equal to, we can just write this as ba f of x dx, but no greater than capital M, see capital M, which is 2 times the interval 3. Now we just have to write it in a better form. 1 times 3 is a 3, and right here our interval ba f of x dx, right, f of x dx, and less than or equal to 6. So that right there is our final answer. What's the final answer telling you? That this specific function, it has a certain area, and that area can be no smaller than or equal to 3, but it can be no larger than or equal to 6. And you can actually figure this out. If you knew how to do integration, you can. And let's do it over here. Assuming we knew how to do this integration, let's find out what the exact value for this interval will be. You'll do the integral of x to the 1 over 2, which is the same thing as root x. And what will you get? You'll get x to the 3 over 2 over 3 over 2. You'll learn all of this. You'll get 2 over 3, x to the 3 over 2, all affected by the interval 4 and 1. You have to feed 4 and 1 over here, and I'm going to do it for you. 4 exponent 1.5 minus 1 times 2 divided by 3. I'm getting here an area of 4.666. That right here represents the true area, but we're saying we don't want to find the true area. We just wanted to find the range of the area. The range of the area is somewhere between and larger than 3, but somewhere less than or equal to 6, and this right here falls very well within that range. And you can also say 4.666 is the same thing as 14 over 3. So the area, the true area of this function within the interval 4 and 1, upper limit and lower limit is 14 over 3 or 4.666, but our goal over here was only to determine what is the possibilities of its area from the minimum to the maximum. And that's all this question was asking. We'll look at maybe 2 of these type of questions, and that'll be the end of this video. But you can see what this whole concept is about. It's the concept of trying to determine where the area is with regards to its possible minimum area and with regards to its possible maximum area, and the true area will be somewhere in between, as you see right here in the example. So let's look at this function over here, tan x. we have to see within this interval of pi over 3, which is 60 degrees, and pi over 4, which is 45 degrees, what may be the possible values of its area. And you know, this is what we're talking about. The area for this function, if you were to graph it, you know what tan x looks like. It looks kind of like this. Within horizontal asymptotes, you have this type of, within vertical asymptotes, you have this type of a curve. And you know, this is 60 and 45 degrees, here is 0 and we have 90. So we're looking at this interval right here in between right here. And this part right over here is what we're looking at. But let's not focus too much here on the graph, because you can graph it using software. We're looking at within that defined interval, what is the possible area under the curve. And you know, our formula is basically this. You have a lowercase length, which is the lowercase m multiplied by the interval, and the area will be somewhere between an interval f of x dx, and it will be less than or equal to a possible largest value of the m, which is the length multiplied by that interval. And for these type of questions where you're trying to just get this rough estimate of where the area lies in terms of this interval, start with the b minus a value. What's b minus a value here? It's pi over 3 minus pi over 4. Pi over 3 minus pi over 4. This is just fraction over here. Common denominator of 12. 3 goes in 12 4 times. 4 pi minus 3 pi, you get a pi over 12. That's your interval. Now let's find the lowercase m. How do you find the lowercase m? You always are looking at f of xi, because this right here is representing your length. You're placing your sample point into your function to get your length. What's your sample point here? The lowest point is a pi over 4. What's tan pi over 4? What's tan pi over 4, which is 45 degrees? I believe that's a 1. Let's bring our calculators to 45, tan it, and it's a 1. Now our maximum value here in terms of the length representation is placing the pi over 3 and getting its value here. I want to get a fractional value over here. Let's look at trigonometric ratios. If you have a 60-degree triangle, you have opposing root 3, you have a 1 and you have 2. So tan of this will be a root 3. Now you have to just do everything in this form. The lowercase m, which is 1 multiplied by the interval pi over 12 multiplied by pi over 12, right, is the area of this function from pi over 4, 45 degrees to 60 degrees for tan x dx, and it will be up to this maximum area of root 3 times pi over 12. You know, we can write everything here in a better format. 1 times pi over 12 is just a pi over 12. So that represents the lower limit area for this. Pi over 12 is a lower possible limit for the area under the curve. And then this right here is root 3 pi over 12. Root 3 pi over 12. That represents your maximum area. But what would be the true area? We can do it. If we do the integration of this, we can do it. We know the integration, and we haven't studied this, but we will. For tan x, if you do the integral of tan x, you get natural log secant x. And you have it within the interval you're seeing, pi over 3 and pi over 4. These are all trigonometric ratios over here. For 30, 60, 90, which is pi over 3, if you have a 60 over here, you have a root 3 over here, you have a 1 over here and 2 over here. For 45, you'll have 1, 1 and root 2. So when you open up this, you're going to do, using these trigonometric ratios, the secant of pi over 3 is going to be a natural log of a 2. And you're going to minus. Don't worry about all these operations over here. For 45 degree, you'll have 1, 1 root 2. The natural log of that will be a root 2. If you were to calculate this in terms of a decimal answer, you can do it with your calculator. You do a natural log 2 natural log minus 2 root natural log, you get 0.346. So the true area within this interval is 0.346. And you can see what this represents. Pi over 12, pi divided by 12, this represents here a 0.2617. And this over here represents root 3 times pi divided by 12. You get a 0.4534. And 0.346 very comfortably falls in between these two. It's larger than or equal to 0.2617, but it's smaller than or equal to 0.534, and we're talking about the area under the curve. So this over here, this formula over here, basically gives you a rough idea of where your true area is falling between this lower threshold of an area and this upper threshold of the area. For the video ahead, this is our last question where we have to try to get a rough estimation of the area for the possible curve within the given domain. This function may have a true domain of minus infinity to positive infinity, but we've limited that infinite domain to a very minute domain of pi to 2 pi. And we have to get the rough estimation such that we know what the lowest level possible area is within this domain and the maximum possible area is within that domain, and the true area lies in between. You know, over here, the very first thing you should do is determine the width of your interval. You can do b minus a, which is 2 pi minus pi, which is just a pi. You can also now determine the minimum, lowercase m, the minimum length. You know, you'll do this as f of xi. You'll take this lower interval and you place it here in place of x. When you place it here in place of x, you have a pi minus 2 sine of pi. You know, sine of 180 is a 0. All of this zeros out. So you just get pi minus 0, which is just a pi. That's easy. Now let's do the capital M, or the largest length. This right is the smallest length multiplied by the width will give you the smallest area. The largest length multiplied by the interval width will give you the largest area, but let's calculate the largest. You'll do 2 pi in place of x's. You'll have 2 pi minus 2 sine of 2 pi, which is 360. You know, again, sine of 360 is the same thing as sine of 180. We can even bring the calculator. 360 sine is 0 because these are the x-intercepts of the sine curve. Anyhow, this zeroes out and you just get 2 pi over here. Now we know a rough idea of what our interval will be. If you do this m multiply this interval, you get a pi square over here. So that's a lower indication of our area for this possible curve. Area below the curve within this specified interval, and the maximum area would be 2 pi times pi will be 2 pi square. So our true area below the function curve within this interval can be some value in between, but I'm curious to see what that is, just for curiosity's sake. And we don't have to worry about how we get it, but I'll do the integration over here. We have to integrate this over here. It's not hard. You have to break it into steps, and these are all things we learn. You'll have this minus 2 sine x dx. This 2 can always be written out here as a coefficient, which simplifies greatly. When you do the integral over here, you basically get an x squared over 2 over this 2 pi and pi. And when you do this over here, the integral of sine x is a minus cosine x, multiplies with this minus 2 to become plus 2 cosine x. Don't worry about all of this, we learn all of this. Now we just have to actually get an answer. We'll do all of this and we'll do all of that. What do we get over here? 2 pi square is a 4 pi square minus pi square is a 3 pi. You're basically doing 2 pi square is a 4 pi square minus pi square is a 3 pi square over 2. 3 pi square over 2 is the first part. Now let's look over here. Plus cosine of 2 pi is a cosine of 360 is a 1. Cosine of 180 is a minus 1. And what's our eventual answer? 3 pi square over 2. 3 pi square over 2 plus 2 times 2 is a 4. This right here will represent our true area. But how do we actually convert this into numerical answers? Well, we know what the values of pi's are, 3.141. Let's do that. Pi square over here is what? If you do this pi and you square it, you get 9.86. Let's write it over here, 9.869. This right here represents the middle value somewhere. Let's do this. 3 times pi squared, 3 times pi squared divided by 2 plus 4, I'm getting an 18.8. 18.8. Let's do 2 pi squared. Pi squared multiplied by 2, I'm getting a 19.739. So you can see over here, this is the calculated value right here for the true area. This right over here represents the lower range of the area, and this right here represents the maximum range of the area. And as I was saying, according to this rule over here, which we've been studying towards the end of our video, the true area lies between the extremes over here, the lower level extreme, the higher level extreme. It doesn't always lie right in between those two extremes. It can lie anywhere in between those extremes, and this happened to lie, the true area happened to lie closer to the higher end of the extreme and much farther away from the lower level of that extreme. And by extreme here, I'm talking about the possible areas below the curve. So you can see all of this has played out before you, how we've done additional questions in this video, how we started with the relationship between the integral form and the Riemann form the limit of sums. Those several questions we looked at. Then we looked towards the end of this video of any function within a given interval. Diagrammatically, I explained how b minus a, this represents the length and the width. Length times width. The smaller length times the width for the smaller area. The maximum length times the width for the maximum area. And these m values are derived by plugging in your sample point, the lowest and the highest sample point within your function to get the lowest length and the maximum length. You multiply that by the interval to get your individual areas, the end area, the minimum area, and the maximum area. And then you can do, if you know the practice of integration, you can get an idea of how good your approximation was, these end approximations to the true value in between. So this was the substance for this video. I hope you enjoyed this video. Next, we'll start getting into the crux of the integration process by talking about integrals of polynomials, or if I find there's another topic we want to talk about before then, we can. But we won't be really talking about Riemann sums anymore. We'll be talking about integrals from now on. I hope you enjoyed this video. Thank you for watching. Have a nice day.